is Anton Levanian, and he will speak about existence of circle packings on certain translation surfaces. And the mentor is Professor Sergiy Merenkov from New York State University. Thanks.
All right, thank you so much for the introduction. So, in the talk, we will discuss translation surfaces, which are certain topological objects. Then we will discuss circle packings on these surfaces, and then we'll move on to our work and what we did during the project. All right, so consider this unit square right here in the 3D plane. We can glue its pairs of opposite sides together. So here we glue one pair of opposite sides, and then we glue the other pair of opposite sides, and we get a torus. And notice that the torus has one hole through the middle, which means that its genus is 1. The genus of a surface is a number of holes through that surface. And this is sort of the most basic example of what a translation surface is. So this is sort of the most basic type of object we will be discussing. All right, so now what is a translation surface? So a translation surface is formed by gluing opposite sides of a collection of polygons P in the complex plane, satisfying the following conditions. So P must have an even number of sides, and opposite sides of P must be parallel and equal in length. So for example, I don't know, is the color coming out better? No, it's coming out the same, okay. So here we have an example of P. This is only one polygon, but we could have more. And notice that opposite sides are color-coded, they are glued together, and they are parallel and of equal length. So one special type of translation surface we will be discussing is a square-tiled surface. And in this case, P is formed by joining a bunch of congruent squares together. So a torus is sort of the most basic type of square-tiled surface, but here is another square-tiled surface. So you can see this picture to the right here is formed by identifying opposite sides of the image to the left, and this surface has 2 holes, so it has genus 2. All right. So now one interesting question we might ask when we are investigating these surfaces is, where do the vertices get mapped? And so if we look at this surface right here, right, we see that the vertices all get mapped to a single point on the surface labeled 2. And this point is called a singular point. So multiple vertices of the polygon are identified to a singular point. And one of the properties of the singular point that is sort of most important is the cone angle. So the cone angle is 2 pi times delta plus 1, where delta is the order of this singular point. So in the image here, we have the cone angle is 5 times pi halves, because there are 5 angles with measure pi halves, plus 3 pi halves, because there is one angle over there, which has, I don't know if you can see the pointer, but which has measure 3 pi halves, and then there are 2 angles each with measure pi. So the cone angle is 6 pi, and the degree is 2. And now that we've talked about singular points, one important thing that we need to talk about before we move on is the metric on a translation surface. So a metric is a function that gives the distance between 2 points in a set. So on the translation surface, the metric away from singular points is locally Euclidean, meaning if we have 2 points that are infinitely close together, the distance between them is given by the length of the line segment connecting them. However, close to singular points, this stops being a Euclidean metric, and the distances start behaving weirdly close to singular points. So that is important to know before we move on. All right, so now we define the concept of a stratum, which will be important not only for classification of translation surfaces, but also for relating the numbers and orders of singular points to the genus. So first off, we have a surface X with k singular points, vi, and they each have order delta of vi. And we also have this thing called the Euler characteristic, which is an invariant that gives certain properties of the surface. For example, one of these properties is the genus. Chi of x, the Euler characteristic, is always equal to 2 minus 2g, where g is the genus of the surface. And we have this theorem that states that the sums of the orders of the singular points plus the Euler characteristic is equal to 0. And if we sort of subtract the Euler characteristics from both sides of this equation, we see that the orders of the singular points form a partition of the Euler characteristic. And this partition defines a stratum denoted by h of kappa, and kappa in this case is the actual partition itself of 2g minus 2. And this stratum is sort of the collection of all surfaces whose singular points form kappa. So, for example, the stratum h of 2 contains all translation surfaces who have exactly one singular point of order 2. And examples of surfaces in the stratum h of 2 are the 3 squared surface we investigated earlier, as well as the regular octagon. Alright, so now we've discussed translation surfaces and their properties, we will discuss circle packings. And the circle packing is a collection of interior-wise disjoint disks or circles on this surface. So we can see here these circles have mutual tangencies. They don't have to, but they cannot overlap. And this particular packing we will call C3. This packing C3 in particular will be important later on in the presentation. And here it is realized on a surface in the H of 2 stratum. So one of the main properties of a circle packing is a contact graph. And this graph corresponds, in this graph, circles corresponds to vertices of G, and tangency points between circles correspond to edges of G. So for example, we can see the circle labeled A is tangent to itself. This corresponds to a loop on the vertex labeled A. Similarly, there are two tangency points between A and B, one on the orange edge right there, I think that's orange, yeah, and one on the pair of blue edges right there, which are identified to each other. That is why there are two edges, one blue and one orange, connecting A and B. And here is a special type of circle packing where we have one circle that is centered at the singular point. So here we have a circle with radius less than 1/2 centered at the singular point, and the total angle of the circle at the singular point must be equal to the cone angle at this singular point. So here we can see all the arc measures of all of the circle sectors will add up to 6 pi, which is the cone angle at this one singular point. Alright, so now we will talk about equivalents of circle packings, and we have these two diagrams right here. So on the left, we have C3 realized on a surface in H2. It's a 3 squared surface. And on the right, we have also a very similar packing that is realized on a 4 square surface in H2. And notice in the packing to the right, the sort of red parts of the circle and the blue parts of the circle, they are all like, they form circles themselves because the opposite pairs of edges get identified together. So these two circle packings, each with 3 circles, actually have the same contact graph. However, we do not consider them equivalent. And to see this, we see that, for example, the yellow circle and the red circle are tangent twice. And there is this segment right here connecting these two tangency points. And there is a similar segment connecting the tangency points of the yellow circle and the blue circle in the diagram to the left. However, the corresponding segments do not intersect in the diagram to the right. So we see this segment connects the two tangency points between the yellow circle and the red circle, and this tangency point connects this segment connects the tangency points between the yellow circle and the blue circle, and they do not intersect. And for this reason, we consider these two packings distinct. And sort of these patterns will be called tangency patterns throughout the presentation, and because the tangency patterns here are different, these two packings are also different. Alright, so now we discussed both translation surfaces and circle packings. We will talk about some of the questions that were investigated during the research. So the first question we investigated is, if we have a square-tiled surface X that is in a certain stratum, can we realize a circle packing on a square-tiled surface Y in that same stratum, but with a different number of squares from X? And if not, can an equivalent packing to the original packing on X be realized on an affine or linear transformation of the surface Y? And the second question we will discuss once we discuss our work on the first question. Alright, so here we have C3 shown above. It is on a square-tiled surface, a 3 squared surface in H of 2. And what was proved in the research was that an equivalent packing to C3 cannot be realized on any 4 squared surface in H2 without applying a linear transformation. Bless you. So here we have two surfaces, and they are four squared surfaces. And sorry. And they are each in h of 2. And on these surfaces we have two circle packings, and they each are composed of 3 circles. And we see that although both of these packings have the same contact graph as C3, they are actually not equivalent because of differences in tangency patterns. So sort of the packing to the bottom left, we already investigated why that was different, and on the bottom right, it turns out that the tangency patterns are also different from those in C3. And it turns out that no matter what packing we have on this 4 squared surface right here, it can never be equivalent to the packing that is on this 3 squared surface, which we call C3. And so C3 cannot be realized on any 4 squared surface in H2. However, if we sort of loosen the restriction that we cannot apply an unified transformation and vertically stretch the surface, the 4 squared surface, by a factor of 4/3, C3 can actually be realized. So we have this right here, this packing. Here we have this, and this right here. They are all the same circle because of the identification of opposite edges, and this packing has the same contact graph and tangency patterns. This was sort of the first big result that we proved. The second big question that we investigated during the research at PRIMES was how complex can a contact graph get on a certain surface in a stratum. So, and we measured complexity with 2 different sort of measurements. One of them is the total amount of loops on a single vertex on the contact graph. And the second one is the total number of edges possible between any 2 vertices of the contact graph. And we call the former multi-loops and the latter multi-edges. So in H of 2, in the genus 2 stratum with just one singular point, we proved that a maximum of 8 multi-loops and 8 multi-edges are realizable on any contact graph in H2. So 8 multi-loops are realized on the surface to the left, and 8 multi-edges are realized at the surface to the right, but 9 multi-loops or multi-edges cannot be realized in H2, on any contact graph in H of 2. So we proved that 8 is the maximum. And we sort of extended this theorem in the genus 2, to a generalized genus G stratum, H of 2G minus 2 with just one singular point. And here it turns out that 4G multi-loops and 4G multi-edges can be realized on at least one surface of H of 2G minus 2. So as an illustration, we have 12 multi-loops in the genus 3 surface H of 4, and 12 multi-edges in the same surface H of 4, stratum H of 4. Yeah. So here we did not show that any more can be realized. So it would be interesting to see if potentially more can be realized. So we did not provide a bound on this complexity as we did in the H of 2 stratum. All right. So then we also took this to the genus 2 stratum with 2 singular points, H11. And here it turns out that 5 multi-loops and 6 multi-edges are realizable on any contact graph, on at least one contact graph in H11. So here again, there is no bound on the complexity, but that is an interesting potential direction of research. And we also expanded this to the general genus G stratum, Hg minus 1, G minus 1, where 2G plus 1 multi-loops and 2G plus 2 multi-edges can be realized on at least one surface of this stratum. So here we have an example in the genus G, the genus 3 stratum, H22. So 2 distinct surfaces, each with 7 multi-loops and 8 multi-edges here. All right, so this concludes the math portion of the talk. I would like to thank my mentor, Professor Sergiy Merenkov, for his guidance during the research. I would also like to thank Dr. Tanya Khabanova, Dr. Slava Gerovich, and Professor Pavel Etingov for this amazing research opportunity, PRIMES USA. And I would also like to thank my parents, my brother, for all of their support, and especially my mom for driving me to Boston from New Jersey, and of course all of you for listening.
Okay, any questions?
say something about the idea of how you achieve the maximum bound?
Can I
H2 phase?
in here?
Yeah. In H2, the reference H.
So how do we demonstrate that this was
Yeah,
a?
what are the ideas behind that?
So here we sort of divided the different possible surfaces in H of 2 into cases. So either square tile surfaces or octagons. There's only a certain number of possible polygons that can be identified to a surface in H of 2. So we actually went through all of these polygons and showed that 9 actually cannot be realized. Questions?
Other questions?
So in this project you studied circle packing. Is there any generalization to things like sphere packing or something like that of higher dimensions?
So a transition surface, sort of, the surfaces we investigated were all 3D surfaces. So by sphere packing, do you mean circles on spheres or spheres on the surface? So, because I don't
It
know.
would be in 3D, that's much more complicated.
Yeah, we did that was beyond the scope of what we studied in the presentation, but I'm sure that would be an interesting potential research direction if there is an equivalent of this surface in higher dimensions.
Yes, thank you.
Can you make any identifications beyond the surface where the lines are parallel and
Can you please repeat that question? Sorry.
can you can you have any pairing of edges you want on the surface?
The edges have to be parallel and opposite edges. They have to be.
I
What do you
think
mean by opposite edges?
they can just asking, is there any combinatorial matching of sides is possible for, is it possible for any matching to draw a polygon, like you said, for which you will realize that matching?
Wait, is that what I meant?
No?
Can you what do you mean by opposite edges? Because in some of the examples of
So, in this case, the opposite edge to this one would be this edge right here.
Yeah, in the previous example, there were more than one edge that was parallel to a given edge, but you assign,
Oh.
there is a matching of edges.
I know what you mean.
Yeah.
So, I think what you mean is that we can potentially realize, identify this edge with this edge.
is that allowed?
So this is beyond what we investigated in the project, but I did see in a couple of papers that this was actually done. So.
Okay, so any matching edges that are parallel and have the same.
They have to be opposite edges. So the surface we studied had opposite edges identified, but theoretically you could identify edges that are not necessarily opposite but are parallel, and if you can that would just be a different sort of family of. I mean, it's the same family, but it would be beyond what we studied in the project.
What do you mean by opposite? Can you do you mean halfway around the surface?
Yes, they're sort of a.
No, it means that the bulk is on the other side.
they form a rectangle?
Yeah, pretty much.
Okay.
That's a very good definition of what opposite means in this case. Yeah. Yes.
Wait, can you go forward side? Wait, to the side with the four, the compass shapes?
Yeah.
Yeah, wait, those sides, opposite sides don't form rectangles.
Oh, not a rectangle. A parallelogram. A parallelogram would be better to describe.
This means that you draw normals inside the polygon, they should be opposite.
Yeah.
Opposite oriented.
Sort of here. If in this case particular, since this is a symmetric shape, the idea of opposite side is pretty easy to define because there's a clear defined notion of a center here of this polygon, and sort of a 180-degree rotation about this center would give the opposite side in this case.
Wait, is there a formal definition of opposite side?
I mean, technically there is, but
If you travel on the outside, then you're going in the opposite direction when you reach the opposite side. You start from the left point, and you travel around clockwise, you're going to the diagonally left when you reach the opposite side.
yeah.
So can one edge have multiple opposite edges?
Each edge is only identified to one other edge, and exactly one other
But
edge.
if they have multiple opposite edges, you just choose one to identify.
Yeah.
Yes, that's what you do.
And if you want to attach to something that's not opposite, you need to twist. Otherwise, you will get something that is not orientable. You
Yeah.
will not get a surface of genus G, but you will get a non-orientable surface like a Klein bottom.
In this case, all our identification occurred without rotations or reflections or anything like that, only translations.
Yes.
Like, in general, like, how do you count the genus of, like, a surface? Like, I don't know if you do.
All right, so in this case, we can actually use the theorem that I'm going to go back. Sorry for switching to this slide, to this board all of a sudden, but in this theorem right here, if we know the number and order of the singular points, then we can add them up here, and that will be equal to 2g minus 2 over here. So that's sort of how we evaluated all of this. So for example, this surface right here, there only is one singular point of order 2. So the sums of the orders of the singular points of the surface is 2, and that is equal to 2g minus 2, so g equals 2.
And the order is counted by looking at the
Cone angle, yes.
square.
Right, but there is actually a slightly simpler way, which is you just count how many points, on singular points on the surface you get. So these are equivalence classes of points, vertices of the polygon, and the genus is related in a simple way to that.
Yeah, this is the method that we use to count the genus, but yeah.
Okay.
Any other questions?
Other questions? Okay.